Hello, everybody, and welcome to our webcast, How to Design an Efficient Compressed Air System, sponsored by Parker. I'm your host, Gary Cohen. I'm very happy to be with you today on behalf of Plant Engineering. Before we get too far, just a few words about the webcast console we're all going to be using today. Please type any questions for our speakers in the Q&A widget located below the slide presentation. Our live Q&A session will start in about 45 minutes. Today's webcast is being recorded, and you'll receive an email with a link to the on-demand event. To download a PDF copy of the presentation and a certificate of completion, use the Additional Resources widget on the right side of the webcast console. Those documents also will be available with the on-demand version of the webcast. And if you need to see things a little bit bigger, you can also expand your view of the slides by using the icon in the top right corner of the slide widget. A few more tips and tricks to help you get the most from today's webcast. If you're experiencing any issues with your slides or with your audio, first try refreshing your browser. You can control the volume of this webcast by adjusting the volume on your own computer or by adjusting the volume on the webcast platform. If you are having technical problems with the audio or with that slide presentation, again, first try refreshing your browser. If that doesn't work, you can click on Help in the top navigation toolbar for additional troubleshooting steps. If it does turn out you need a technician, just type a message in the Ask a Question box and the tech team will get to you as quickly as possible. Any individual user experience questions, I can't hear the audio, I'm not seeing the slides, those will be answered in the Q&A widget below the slide presentation. All right, now we get to the good part where I get to introduce our wonderful speakers for today. Tim McDonald is a business unit manager at Parker and a seasoned technical sales and support professional with 30 years of experience specifying and selling rotating equipment and related piping systems. He spent 9 years focused on process piping systems and 21 years supporting rotating equipment and the associated piping that integrates and optimizes those systems. Tim's customer-centric background spans application engineering, system specification, and field troubleshooting across diverse industrial environments, giving him a practical perspective on how piping design choices impact reliability, safety, energy performance, and total cost of ownership. He holds a Bachelor of Science in International Business and Finance and a Master's in Finance. We also have Jody Panzer, who serves as a regional sales manager for Parker's Transair product line. In his current role, he works with distributors, mechanical contractors, engineering firms, and manufacturers to deliver engineered solutions for compressed air, inert gas, and vacuum piping systems. With more than 20 years of experience providing successful system solutions across diverse U.S. market segments and industries, Jody brings hands-on application expertise in system layout, material selection, pressure drop management, and installation best practices. His previous compressor industry experience includes partnering with compressor OEMs and end users on system audits, sizing, and performance optimization to improve reliability, energy efficiency, and total cost of ownership. All right, that's it for me here at the beginning. Jody, I am happily handing things over to you.
Gary, thank you. And welcome to everyone joining us today. This afternoon, we're going to be discussing components of a compressed air system, distribution piping, materials, and connection types for an efficient system costs of ownership and energy efficiency. And Tim's going to go over some design considerations to help reduce cost of ownership. And of course, Gary mentioned we're going to save some time for Q&A and some resources at the end. So many people in plants don't realize that compressed air is one of the most, if not the most expensive utility in a plant. When thinking of compressors, a lot of times it's thought of just the upfront cost, but actually if you look at over 10 years, the equipment may be around 12%, preventative maintenance 12%, but really the electricity costs can average up to about 76%. Inefficiencies waste energy and unfortunately shorten the life of equipment. On the flip side, an efficient system, it can result in 20 to 50% in energy savings. We want to have an efficiency system, and that's going to help you improve uptime, limit scrap, and product quality will, of course, be going up for you. Let's have a little discussion about system of equipment and an overview of the equipment going into the system. So here we're looking at an overhead view of a typical plant. We have the compressor room, where you're taking ambient air, you are compressing it, going through some air quality control equipment to clean up the air on through to your distribution. So you're taking that energy that you just created and converting it into work. When thinking of your compressor system, don't just think of individual pieces of equipment. Think of it as a whole. We're going to discuss life cycle costs. It's, as I mentioned previously, it's not just the equipment that you're paying for right now, maybe using your CapEx. It's the whole system, how efficient it is. So there are many options in regards to industrial compressors to choose from. Let's go over your most frequent ones used. First, we have reciprocating compressors. These are small, 5 to 25 horsepower, typically use pistons, very high oil carryover. They have a duty cycle, so you do not want to be running these compressors full on. They need time to cool off, otherwise they will fail prematurely. And like I said, that oil will carry over into the airstream. Then we have scroll compressors. Very quiet, oil-free, very good for, they use spiral scrolls to compress the air, very good for HVAC systems and dental offices, very small load and some healthcare. Rotary vane, small to medium, good for continuous loads. Then rotary screw compressors, which are going to be your most common compressors found. Those come in oil-free, oil-flooded, single-stage, two-stage machines, range from 5 to 1,000 horsepower. Very efficient compressors. Then if we need a compressor exceeding 1,000 horsepower, anywhere from 2 to 300 on up, a centrifugal is the right way to go. Those are going to use high-speed impellers to compress air. So a couple tips in regards to compressors. Always avoid excessively oversizing your compressors. You want to size for your typical load with some margin for growth and for your peak time. How do you figure out your peak time? You can get an air audit done where they're going to place sensors around your plant for a couple weeks and give you a very good air profile. You'll see where your peak loads are and where your leaks are as well. So you never want to oversize. If you're sized for 100 horsepower now and you believe in 10 years from now you're going to need maybe 500 horsepower, we don't want to do that at the current state because that could cause premature failure. And as I mentioned, your energy is not free that you're using. That's where piping comes into play. It's a lot easier to do larger piping early on than doing that later. You can always add another compressor. There's many different controls with compressors. You have start stop where the motor's coming on and off. You have load unload where the motor's continuously running, but you have a pressure band where it loads and unloads. Consider having a variable speed drive in your system. That motor is actually designed to meet the optimal air demand. That will contribute to significant energy savings, but also note you only want one VSD in your system. If you have multiple ones, they're going to fight. Even with good controls, they're going to fight to see which comes on first. So there you see, and I mentioned oil flooded, oil free. What does that mean? So oil flooded, or oil injected, you're injecting oil into the compression chamber and the crankcase where it's going to lubricate, it's going to cool, and it's going to seal moving parts. Unfortunately, by a byproduct, some of that oil is going to carry over into your airstream. Even with filtration, it could carry over. So you need to avoid this in regards to sensitive applications, healthcare, food and beverage, semiconductor, pharmaceutical. There are food-grade oil options available, but note that those will degrade faster and it will require more maintenance and more oil changes. Oil-free, on the other hand, for those sensitive applications can be used. Oil-free, there's only oil found in the crankcase, nothing in the compression chambers, typically a two-stage compression system on the rotary screw side, and there's no possible contamination that can be found. One thing to note, there are going to be a higher upfront cost, but life cycle cost is going to go down. Your maintenance costs will go down as well. Also, these compressors create a tremendous amount of heat. So there's a couple ways to dissipate that. Air-cooled or water-cooled. You get to a certain temperature and water-cooled is the only option. So storage. What is storage going to do for us? We know that real estate is hard to find, but to have an optimal system, you want a wet tank and a dry tank. That's going to help buffer demand. It's It's going to stabilize pressure. It's going to reduce the compressor and your dryers from cycling too much. What is a wet tank? Wet tank is going to be found right after your compressor, before your dryers and filtration. Some of that condensate that you're going to create from the compressor and oil carryover is going to go to the bottom of the tank, and it's going to sit there. Please consider, when having a wet tank, to possibly epoxy internal coating it. Otherwise, it will corrode over time. Then we can get through our dryers and filtration and go to a dry tank. That's going to also help buffer demand. Both tanks will require a pressure gauge and a drain. You can either have a manual drain or a zero loss drain. A zero loss drain is not going to use any expensive compressed air to eliminate those contaminants. Dryers. What are the purpose of dryers? Water condensation is a natural occurrence and byproduct of compressing air. It's inevitable. We need to get rid of as much as possible. Yes, we have the tanks that I mentioned, but that's just not enough. The typical dryers used are refrigerated dryers. That's going to get you between a 35 and 39 dew point Fahrenheit. Can even go higher than that, 40s, 45, depending on the ambient air. You can do cycling, non-cycling, VSD dryers. They all have their costs associated and their efficiencies associated with them. If we need a dew point that is always the same, a desiccant dryer could be the way to go. That can get you a negative dew point, negative 20, 40, even negative 100 with certain technologies. They run on a 2-tower technology. So one of the towers is drying the air, while the other tower that has been saturated with moist air is regenerating. There are economical ways to go about that as well. You have a heatless dryer, heated, blower purge. A heatless is going to be your most economical. But this is when we look at, and we're going to touch on this a little bit, on life cycle costs. So it's most economical up front, just like your oil flooded, but a heatless is actually going to use compressed air that you're paying for to regenerate that saturated tower. So we need to think of the full cost, not just your upfront costs. Then we have a deliquescent dryer. That's going to use saw tablets similar to desiccants that use a silica gel. They use salt tablets, and when they're saturated, they need to be changed out as well. Then good point of use, very low flow, but moderate dew point options you can do is a membrane dryer. Very good for point of use. Note to size the piping in the compressor room to the manufacturer's parameters. We don't want to be squeezing, causing any unwanted pressure drop in our compressor room. Then we have filtration. What is the purpose of filtration? We're going to try to eliminate more processes, some oils, particulates, and vapors from our system. First, we have a water separator. A lot of these will remove excessive bulk amounts of water and liquid oil. Many of those are found internally inside of your compressor. Then we have a coalescent filter that is going to remove particles as well as oil and water. Particulate filters, that's when we can get down to the smaller micron level. So you can choose your micron level in your filtration to get rid of tiny microorganisms and particulates. Then absorption, that is going to remove more oil vapors if you're using an oil flooded compressor, typically with a carbon filter. Then if oil is contamination cannot happen, cannot go into the airstream, you might want to go with an oil mist eliminator. That's going to be a more heavy duty coalescent filter. One last note on filtration. If you have a desiccant dryer system, have a coalescent filter before the dryer, so a pre-filter, and then after your towers, put in another finer coalescent filter and a particulate filter. Why? Because you're blowing compressed air through these dryers. It's going to shake up that desiccant a lot, and some of that dust particles are going to come over into the airstream. You want to catch those as much as possible so we don't, it doesn't go down our stream. Piping. Why does distribution piping matter? Well, our goal is to deliver clean air, stable with minimal pressure drop. You're paying for every bit of pressure drop. Hopefully by now we have created a good clean air system, but we have to think about the piping materials and the diameters associated with that. What are our typical materials found in a plant? Aluminum and stainless, very good for corrosion free. And we're going to go into more details in this in the upcoming slides. Carbon steel, very cost effective, readily available, yet longer labor times and corrosion risk is extremely high. Then copper, very good for smaller bore diameters, a lot of times permanent fittings, welded, soldered. And there's HDP composites as well, which are lightweight, but temperature limitations and pressure limitations. Velocity, Tim's going to touch on some scenarios with velocity comes into play later, but when sizing your header, try to maintain between 19.7 and 32.8 feet per second. On your drops, no more than 30 feet per second. We also want to consider minimizing T's, longer radiuses when you're making a turn, because every time you deadhead and do a sharp turn, you are going to cause pressure drop. So even in the compressor room, as you're heading up to the header, you might want to consider a Y or just a slope. Why does selecting the right distribution pipe matter? So with everything we went over, you design your system, you have the perfect sized equipment for right now and for future needs, but we have to consider the diameter and the piping material being used. Let's think of and talk about why undersized piping will affect your system. Well, first of all, distribution systems can account for 20 to 30% of losses. That's between pressure drop and leaks. There are certain piping systems and fittings that with expansion and contraction, it's a natural occurrence, will leak over time. We want to limit that as much as possible. It's going to impact energy use, equipment life, and product quality. We want to have as much uptime as possible. So with undersizing pipes, that's going to create more friction and resistance, causing significant pressure loss from the compressor to the point of use. To overcome pressure drop, what is typically done? Well, you may need 85 PSI at your equipment and your compressor's running at 95 and some of the your equipment is starving for air or pressure. The typical thing that an operator will do is go to the compressor, see that it's at 100 PSI, and they're going to turn that internal controller up to 125, or maybe max pressure is 150 PSI. Not thinking about the piping that may be designed incorrectly, maybe it's undersized, maybe there's corrosion within it that is causing back pressure and your compressors to run harder to overcome that. But with every 2 PSI we increase, that's going to cost 1% of energy costs. And also consider, when you are making changes in elevation, you're going to have to overcome, your air has to overcome gravity. So that's going to cause your compressors to run harder as well. And let's consider gradual changes in elevation. So pressure drop sources, as we mentioned, friction. Friction is the resistance to flow caused by the interaction between compressed air and the internal wall of the pipe. Consider your fittings and valves. So everything in a compressor system has somewhat of a pressure drop associated with it. In your compressor room, even the dryers, the filtration we mentioned, they all have a pressure drop. We want to minimize that as much as possible. So your fittings and valves, try to have as much full bore as possible. As I mentioned, elevation changes and condensate management, make sure that size adequately. We want to have as much of a laminar flow as possible. Very hard to achieve, but it can be done. Otherwise, turbulent flows with internal rust and corrosion and many different changes and T's will make it more turbulent, and you're not going to get the pressure that you need at your system. Mentioned before, minimize elbows as much as possible. So here are the materials that are typically found in piping systems. So we have carbon steel, very high strength, but the corrosion risk, as I mentioned, is going to happen over time. Unless you're using a desiccant dryer, no condensation is happening within your pipe. Corrosion will happen over time. Typically welded, press fittings, and threaded. Those threads with expansion and contraction, as I mentioned, will leak over time as well. Stainless steel, extremely corrosion resistant, very high purity, but upfront cost is a little higher and labor times are up as well. Aluminum, extremely smooth bore, corrosion risk is very low to non-existent, extremely lightweight. Your labor times are significantly reduced. And, on typical piping systems, what you want, the air that you put into your pipe is the air that you want at your equipment. You do not want to be adding any contaminants to the air. A proper piping system will not do that. Copper, corrosion resistant, very clean. requires specialized labor. Then we have HDPE or PEX composites, plastic composites, very lightweight, modular, does have temperature limitations and sometimes specialized equipment to glue them together. Then PVC, that is just never allowed in compressor systems. We never want to have PVC. Under cold conditions, it will crack, and under hot conditions or even UV light, it can soften and your integrity will be compromised. So here we have a chart for you to refer to. This presentation is going to be available after this, and please refer to this for your current or future projects. This will help you choose what piping system might fit your application. You see there's some similarities here, some pros, some cons, except for PVC. Aluminum, let me touch on that real quick. This is where life cycle costs come in. You see the upfront costs might be a little higher for aluminum and the fittings that go along with it, yet your installation times could be 50, 60, 70% less. So that needs to be considered, and also with no corrosion. Diameter range on the aluminum as well, there's some limitations there, but aluminum will cover 95, 96% of all industrial projects. When we get into the 14-inch range and above, that's when you may want to look at steel. Here's the connections associated with the piping systems. We have threaded, as I mentioned. Very common, very readily available, will leak over time. Soldered or welded, very good, permanent typically, requires specialized labor, maybe even firewatch in certain areas. Press fit fittings, very fast and reliable. Great sealing internally, usually, so you can't replace the seals. Does require specific tooling. Then groove technology, very common, very fast install, has some pressure limitations and requires precise grooving. Clamshell, very common, replaceable seals, a little bit slower installation, and does require some infield grooving or lugging. Then push to connect fittings, extremely rapid install, easy to modify. There's just some temperature and pressure limitations to that, but it can cover, typically push to connect can cover, typically goes up to 1.5 inch, can cover to the 232 PSI. Then here is another chart to refer back to when you're considering the connections to go along with the piping system you're choosing. Some of them match up with each other more than others. Push to connect, I'd like to make one note on that. Many manufacturers claim to have push to connect, but when you put the push to connect fitting on the pipe, you have to torque it or tighten it. That's not true push to connect. True push to connect, you should mark for the depth on the pipe and just take the fitting, insert it into the pipe, and that should be it. There should be no torquing or turning, only when you need to release it off the pipe for modifications or adjustments. So ISO standards, these are guidelines and specifications for product services to determine and make sure that their systems are reliable and safe. They range anything from IT security to air purity, filter performance. How do we get to an ISO standard with filter performance? It may be on the micron level that you have to choose, or maybe multiple filtrations within the system to reach these certain ISO standards. ASME will cover your pressure vessels, steel, and a couple notes on that. In regards to California and Canada, that can be a little unique in their requirements. Canada is done by Providence, and they use a CRN code. Just check with your local ordinances and municipalities. They'll let you know about their requirements and what you need to do to meet those. So that being said, we went over the equipment portion and what is how vital it is to the operation, not just the upfront cost, but the whole life cycle cost. Now Tim's going to touch on design considerations to have an efficient system.
Thank you, Jody. Thank you for presenting all that information for us. Let's take a quick dive into design considerations when looking at an efficient piping system. Some of the main things you want to identify right away is your demand profile. When you're looking to put the right size piping and the right type of system into your facility, you need to know what the total demand is, air consumption for your facility. You identify those processes, tools, and cycles that use air. What you need to find a baseline, what's our base load, what's our peak requirements, Is there variation between shifts or seasonal work? And it's important to have that. It also lets you know what the lowest pressure setting you can set that compressor at and still get all the work done. Remember, the lower you can set the setting on that compressor, the less energy you'll consume. And as Jody had touched on earlier, 75% of the life cycle cost of a compressor is the energy it consumes. We also want to identify misuses of compressed air. If we have locations within the facility where you have inappropriate use of compressed air, you've got employees blowing themselves off with air at the end of the shift, or they're cleaning their work surfaces with compressed air, that's all energy that's being consumed. There's a cost associated with that. And you also want to remember, when you're specifying pipe, consider future demand capacity requirements. Jody touched on that a little bit, but it's important to think about what's the future state of the facility going to look like. I can size piping today for the current demands of my facility, but if I know in 2 to 3 years from now, we're going to be putting an additional 100,000 square feet on the back, or we're going to be increasing our production within the same footprint we have, we might want to take that into consideration now. It most likely will be less cost to put a little larger diameter or next size up pipe into the facility now than it would be to try to come back in the future and run additional piping, and or not do anything with the piping, and to incur that pressure drop across the system as the demand has increased, but the pipe diameter has not. So artificial demand, what is it and how do we want to reduce it? Jody touched on this a little bit. Lower system pressures to the minimum level so you can save as much energy as possible. Remember, for every 2 PSI is 1% of the compressor's energy usage. We've touched down on that a couple times, but that's really important to realize. There's a lot of energy consumed when making compressed air. It's not super efficient technology, but it's a necessary technology. It's in the plant. Use point of regulators where only they're needed, okay? Again, we want to minimize flow across any kind of restriction. Improve your storage. Jody touched on wet and dry receivers, right? You need to be able to ride through the peaks without raising the set point on your compressor. What that means is if you have a momentary demand or spike in your system, it's better to draw off that storage tank than it is to fire up that compressor and try to make it catch up. And controls, right? Sequence compressors so only the necessary units run. Jody touched on it a little bit, but if you have multiple compressors in your facility, ideally you would want a base load with a fixed speed machine and then trim with a variable speed compressor. That allows you to get the right amount of output with the minimum amount of energy consumption. And always find and fix the leaks within your facility. Leaks cost money. Start with the largest ones you know you can find, and then also work in your most frequently used zones within the facility. We want to minimize the leaks. We want to minimize the amount that compressor has to run. So let's talk a little bit about the piping layout and the materials to minimize that pressure drop across your system. Typically, we find 2 types of systems in any facility. One would be a closed loop system where you come out of the compressor room up to a header, go around the facility in a complete loop, or you'll find a linear design. There's advantages and disadvantages to both types of systems. So let's talk about that briefly, right? In a closed loop system, there's lower chance for pressure drop. You also can feed the plant in 2 directions coming out of the compressor room. If necessary, piping can be sized to provide for additional air storage. It also allows for easy future expansion. Some of the challenges with the closed loop is you do have higher material and installation costs because you're doing a complete system now as opposed to a linear run. And you have a little bit more complex system design when you're putting the system together. On a linear design, on the other hand, you have lower material and installation costs. You may have less than half of what you have in your closed loop system. Less design complexity. Makes sense, right? There's less machines you have to feed. There's less piping you have to worry about. Easier maintenance, isolation. So it's always important to remember when you're working with a header or any type of distribution system, you want to include isolation valves in that header that allow you to maintain production in a given area while you may isolate and de-energize a portion of the facility. If there's work that needs to be done, machines that need to be moved, it may be necessary to isolate part of that header. So putting those isolation valves in early on makes this a much easier process. Okay. It's also easier to expand a closed loop into a loop system from a linear system. Some of the challenges with linear system is you do run the higher chance for pressure drop out of the compressor to the point of use, and you're only feeding the plant in one direction. And so just to reiterate a couple of things that Jody touched on, branch takeaways from the side of the main with big sweeps, if you can, 45s versus 90s, because we're trying to eliminate that frictional loss in your system. And there's two ways that happens. One is with air molecules impacting the inside of the pipe. The other is air molecules impacting each other. We want to minimize the frictional losses in the system so we have less runtime on that compressor, but the maximum amount of work gets done. And hot tapping pipe also allows you to be able to work on a system without de-energizing it. So in some cases, you can add a valve body, you can add a lateral, or you can change direction off a main by hot tapping the pipe while it's still pressurized. There are systems that do allow this, and this prevents from having to shut the system down and de-energize and then re-energize the system at a later time. Piping layout materials to minimize this pressure drop. Corrosion resistance is vital, okay? We all know black pipe is the cheapest. It's the easiest to get a hold of. Every contractor out there knows how to work with it. But over time, unless you have a really strict regimen in your compressor room with your air treatment equipment, you will get condensate carryover. You will get moisture carryover into your black pipe. Over time, that will rust, that will degrade, and that will create issues for you as far as air quality and frictional losses in your system. You always want to use full bore piping and fittings. So you may not think about it, but if you have a couple thousand feet of header in your facility, and at every 20 foot you have a joint or a union, you've two things to consider. One is you have potential leaks at these joints and unions, and the other is if you do not have full bore design with the fittings or the connection technology you're using, even if it's just fractional, each one of those joints and fittings has the potential to be a frictional loss, to create a turbulent airflow or more turbulent airflow, and then create pressure drop across your system that ultimately you may have to reset the set point on the compressor to overcome. Reduce pressure drop to the system. Long radiuses whenever possible. Use 45s over 90s when the space does allow. Use Ys over Ts to reduce losses. As Jody mentioned, avoid sharp corners whenever possible. Okay, and safety first, never use PVC pipe. We will harp on that a couple times here during this presentation. Never use PVC pipe in a compressed air application. It's not safe. You run the risk of injury to personnel and damage of equipment. So let's talk a little more about design considerations when we're laying this pipe out. And we remember, again, the goal here is we want to minimize pressure drop across the system, right? Design targets when designing a system. Ideally, you want to have a 5% total system loss or less in pressure drop end to end when you design a system. Now, if you have any questions, your doubts about that, upsize the pipe a little bit. You may lose a little bit of velocity in doing that, or maybe that's a good thing depending on what your initial calculations were. But a 5% pressure drop is probably ideal. Any more than that, then you run into the issue again of more power consumption. Less than that, if let's say you design a system and you wanted zero pressure drop in it, a couple of things come into consideration. Your initial cost to install that larger pipe, and you've also got, you may not have the gas velocity that you desire to carry any contaminants or moisture to the point where you want to get them out of the system, for example, a drip leg, okay? Keep branches short and balanced. Takeoffs from the sides or the tops, again, and use sweeping tees whenever possible. Segment the loop with full port block valves for isolation. Touched on that briefly. If you need to de-energize only a portion of the pipe, it's best to have a couple valve bodies in place so you can do that as opposed to shutting down the entire system. Okay, provide takeoffs, again, drops with ball valves and drip legs. If you're working on a specific piece of machine, you need to be able to isolate that piece of machine. You need to be able to de-energize between that drop and that piece of equipment. So you need to make sure you have the right equipment in place that allows you to do that, to make sure you're meeting the OSHA standards for keeping everybody safe. So let's talk a little bit about velocity. Jody's touched on it. I touched on it. It is kind of critical when we talk about compressed air systems. You want to size to your velocity targets first. And what we mean by that is when you're sizing your pipe, the two things you really want to take into consideration is obviously total system pressure drop and gas velocity. Too much velocity is a bad thing. Too little velocity can also be a bad thing, right? So basic guidelines are, in your compressor room, you want to keep your gas velocity to 20 feet per second or less. And the reason we specify that, which is a little bit lower than what you would do in your headers or your drops, is you've got manufacturer requirements coming from your dryer manufacturers, your filter companies, your separator companies. They all have specific targets, pressures, and flows they want to see, or air velocity through their pieces of equipment. So we want to be careful not to overrun those pieces of equipment. We want to make sure we get the maximum usage out of those pieces of equipment. You're going to have a little bit of pressure drop across those pieces of equipment, but we don't want to have so much gas velocity that we carry moisture, that we carry oil beyond the designed equipment that takes it out of the system. In your distribution header, ideally 30 to 33 feet per second is ideal. If you're higher than that, you run a couple of risks. You can damage the equipment that's being operated pneumatically. It's rough on seals. It's rough on actuators. If you have probes or sensors inside the compressed air system, they may not give you an accurate reading if your gas velocity is too high. On the other side, if your gas velocity is too low, one of the risks you run into is not being able to carry contaminants and moisture downstream to the proper discharge location. Point of use drops. So let's say you're coming from your header and you want to go down to your drop, to your piece of equipment, to your workstation. 30 feet per second is ideal. Why does this matter? Higher velocity raises resistance, right? We want to minimize the resistance. We want to keep the compressor set at the lowest pressure point possible, and then maintain that throughout the day or throughout the shift. If you're running 3 shifts, it'll be continuous, okay? If we have frictional losses in the system based on high velocities, we've got to overcome that with the compressor, which means we have to consume more energy to make that happen. So make sure you understand, takeaway on this slide is make sure you understand the air treatment manufacturer's guidelines when sizing pipe in the compressor room. Every piece of equipment in that compressor room, on the discharge side of that compressor to the point where you're actually going out into the header, there is a recommended pressure, flow, velocity that each manufacturer comes up with for that piece of equipment. And if we size the pipe properly in the compressor room, then we can maintain that. So oftentimes you'll see 4-inch piping in a compressor room, but you only need 3-inch piping in the header. The reason why we upsize in the compressor room is we want to keep that velocity down to acceptable levels. All right. So let's talk a little bit about sizing basics. Okay. What do we need? We need the system inputs. Okay. Now I will tell you, there are a lot of design calculators out there. We have one on our landing page. There are different types of tools you can use that does this for you very quickly. It's a very simple process, but you need to know what your inputs are going to be in your system. What's our desired pressure, right? That all comes from your demand profile. What's our desired flow, right? Pressure is our ability to do work. Flow is our ability to continually do that work. What's the length of the system? What's the furthest point from the compressor that you're going to be in the facility? Okay. And then what kind of system do we want to put in our facility? Do we want a closed loop system, or are we going to go linear? Okay. Other considerations, what are we conveying? Is it compressed air? Is it some sort of inert gas? Is it going to be a vacuum system, right? The other side of the equation. There are sizing calculators and software to easily calculate this for you. Okay. So set your design parameters, understand what you want, go ahead and start playing with these sizing calculators. And I think you'll find that you can quickly come up with the right size pipe that will best work for all of the inputs you're going to need in your system. Okay, let's take a moment and just talk quickly about a couple scenarios. So here's our baseline. We have a facility, it's 100,000 square feet, manufacturing. We got 125 PSI system pressure. We know that's what we need. We're going to do a closed loop main. We're going to have drops going down to our workstations or our pieces of equipment. We've got 1,000 feet of piping. We're going to have 300 joints. Now, remember what I talked about. Every 20 feet, you're going to have a connection point. Everywhere you have a 90, you have going around a piece of machinery, a 45. Everywhere there, you're going to have a connection joint. So it's important, as Jody said, to understand your connection technology, and don't let that be a factor in preventing you from having an efficient system. All right, we got a labor rate, $95 an hour. Okay, we have our unit costs, time per joint assumptions. We're gonna make some assumptions here about how much time it takes to make each connection. And then we understand that there's additional equipment that may be needed. we've got stainless steel or carbon steel pipe. You've got extra pieces of equipment. You've got heavier pipe. You've got to move it into place. For a high density polyethylene product, you're going to need fusion machines. You're going to have to make connections on that pipe. For aluminum connections, for aluminum systems, you may need special tooling as well. That all has to be taken in consideration when you look at material costs, labor costs, and any special equipment costs to do that. So in this scenario, we've got a new build. This is a specific section of building, normal installation conditions, okay? You'll notice here your material costs are going to be lower with carbon steel. Right? Carbon steel is ubiquitous in the industry, right? We see it everywhere. Everybody knows how to work with it. Also, a low cost would be high density polyethylene. That's an inexpensive material as well. But when you start to put the other parts of the equation together, in this case, labor and extra equipment to make all of this get into the facility at the proper location, let's say you're running 30 feet off the production floor with your header, then when you take your labor and material costs and you combine that, you'll notice that maybe carbon steel is not necessarily the best deal, right? While material may be cheaper, you're going to have significantly more higher labor costs. And so when you look at that, your best options are going to be high density polyethylene or an aluminum system when taking in labor and material costs. Now, you have to maintain those systems, right? So if you look at a 5-year total cost of ownership of that exact same system, you'll see that aluminum comes out significantly ahead of any of the competitors. In most cases for an aluminum system, unless you have to make modifications like adding drops or reconfigure, which you can do with an aluminum system, there's nothing that you have to do as far as maintenance based on the material that's used. It's pretty much a plug and play system. So scenario 2 would be retrofitting an occupied facility, okay? Again, you can see your material costs. Now, when you're retrofitting an existing facility, your labor costs and your equipment costs may be a little bit higher because you've got to work around existing equipment, or maybe you've got production that's already going on. So it's not as clean to get in and out. Your contractors are not going to be able to move as quickly in a facility like that. Also, you need to consider when you're commissioning the system, if there's any type of work that's done with the piping system where you are welding or soldering or doing any type of work, hot work that produces any kind of byproduct gas or fumes, you need to purge that system before you commission it with compressed air. Okay, you need to do a nitrogen purge on that system. It's not difficult to do, but it does take time, and there is a cost associated with that. So that's part of the equation, and this is also true with the new facility as well. If you're going to weld stainless, or if you're going to go ahead and do anything like purge a system or anything, or weld a solder system like copper, you need to be able to purge that system before you actually commission it with compressed air. So let's talk a little bit about what I think is the best option here. So Parker's Transair aluminum distribution system. It's fast and it's safe to install. Okay, you're going to save, as Jody said, in some cases up to 75% labor over traditional piping systems. It's got superior flow and energy efficiency. Okay, you got a natural aluminum oxide coating on the inside as a byproduct of being manufactured out of an aluminum slug. Okay, long-term reliability, air quality. This system will not impart any contaminants into your system. So what I'm saying is whatever the quality of air that comes out of your compressor room, even if you have an ISO specification, that's the quality of air you're going to get at your point of use, okay? Modular flexibility. So one of the great advantages of a system like this is you can take it down, you can reconfigure it, you can reuse the pipe, you can reuse the fittings numerous times. If you use a press fitting or if you weld pipe together or a solder pipe together, you're going to have to cut the fitting out, right? There's costs. Those fittings are no good anymore. You're going to have to redo that work. Working pressures, up to 4-inch, 232 PSI, 6 to 8-inch, 188 PSI. Your working temperatures are -4 to 140, and we do almost a full vac, 99.9% vacuum on the system. There's over 750,000 global installations of this product and 20 years of product innovation. It's a trusted brand in aluminum compressed air piping. So let's talk a little about the connection technologies here with the few minutes that we have left. We've got push to connect, snap ring, clamshell, and groove. We can provide piping everything from 1/2-inch to 8-inch. The reason we use different connection technologies is we want to maximize the safety and non-leak performance of the connection, as well as minimize the amount of labor it takes to make these connections. With your push to connect connection, it's just that very thing. It's like a shark bite fitting. You take the fitting out of the box, you push it on the end of the pipe. You've got 16 stainless steel teeth that hold that into place. It is 100% reusable. It's one of the quickest installation technologies in the market today. Snap ring, we use a snap ring design on the end of the fitting for our 2 and a 2.5 inch. Jody touched on clamshell. We use that for 3, 4, and 6 inch. And then for 8 inch, industry standard roll groove technology and fitting. So what are the key takeaways here? Why distribution design matters? Energy is 70–80% of the compressed air system life cycle cost. Distribution sets require compressor pressure and drives losses, okay? So if you design the system efficiently, including the size, to include your velocity, to include your pressure drop, you're going to maximize the life cycle out of your compressor. You're going to minimize the amount of energy you consume. For every 2 psi in pressure drop is 1% increase in energy consumption your compressor is going to consume to overcome that pressure drop. Again, we size it properly, we design it properly, we minimize the pressure drop through the system, we minimize the amount of energy we consume. We're always going to consume some energy, but we're going to minimize the amount we consume, okay? Other things to consider: downtime, the quality of the air, how much maintenance you have to do on the facility, moisture carryover, corrosion if you use a traditional piping technology, unstable system pressures, all impact the piping system, all impact the amount of work that gets done and the quality of the product that's being produced. There are engineering tools available for you to review. Please go to www.parker.com/Transair. You'll find there's an engineering tool set there for you. We've got CAD files, we've got Revit files for you. We have a spec submittal form already completed. We've got design software available. And of course, we have sizing calculators as well. So at this time, I guess we're going to go ahead and open it up for any questions that you might have on the presentation that we just provided.
And why don't you go ahead and answer some of the questions in the...
Sure, great, thank you. So one of the first questions I have here is, can I design a system with 0 pressure drop? I believe, yes, you can, but some of the things that you have to take into consideration is to get a 0 pressure drop system, the size of the pipe that you would be required to install in your facility may be significantly larger than you need. It also may prevent you from getting the proper velocity from the gas that you're trying to move through your system. So I don't know that you would gain as much from that as might initially be thought. Yes, I think it is possible. You can design a system. Let's say, for example, your system needed you have a small facility or shop and you needed an inch or inch and a half header to feed your pieces of equipment from your compressor, and you decide, well, I'm going to put a 6-inch header in. Yes, you could certainly do that, but what you would pay up front in CapEx for the equipment and what you would lose in the benefit of having at least the appropriate level of gas velocities, I think would not be in line with the benefit you're seeking out of that.
All right, gentlemen, I am back on. Sorry for the audio glitch. We'll take another question here. What should I do if I have limited CapEx funding available when initially designing a system, but I know that there will be an expansion in the future?
Well, I'll try to answer it the best I can. There are other options. When you say limited CapEx, if we're talking about the complete compressed air system, there are options commonly referred to in the industry as air over the fence type systems, where you don't actually have ownership of the compressor itself, where you actually just pay for the compressed air that's generated and your facility utilizes. And so that really can significantly help with the CapEx portion of it. So all you're doing is paying for the compressed air. You're not having to lay out to buy the equipment, and that could include the piping as well. I would say this though, if you know the future state of your plant is going to be significantly different than what it is today, I would make sure that when looking at that CapEx project, you include sizing for what the future state is. So that may mean instead of a 2-inch header, you may need a 4-inch header, or maybe instead of a 4-inch header, you may need a 6 or an 8-inch header, right? That might be an extreme example, but the efficiency that you will then have in the system long term will greatly outweigh any potential losses or CapEx that you save initially. So there are other ways to get new equipment to include piping into your facility besides just buying it outright. If your organization has a compressor manufacturer or local distributor that you're currently working with, I would highly recommend you talk to them about this type of ownership, where you're only paying for the compressed air you consume.
Got it. Can I adopt Transair to an existing system that isn't aluminum?
Yes. Yeah, we can adapt to any system and vice versa. So on the smaller sizes up to 2.5 inch, we're going to use an MPT threaded connector. So there's a couple options that we offer. On the MPT male threaded connectors, you're going to have MPT on one side in multiple sizes, and then Transair on the other. So it's going to be one piece fitting that will adapt. Okay, and we do this often. Then when we get to our larger sizes, we're going to go to a flange. But any system can adapt to us, and we can go to any system.
Perfect. Are all aluminum piping systems compatible with each other?
No, they're not.
The short answer is they're not. And a lot of it has to do with the OD of one manufacturer's pipe and I will say the ID of the fitting that may be going around the pipe. There are enough manufacturing variances that I would be concerned. I would not recommend using one system versus another. The only time that I would do that is if you had a mechanical connection. So let's say you went from one system, you went into an MPT or into a flange, you came out of that with a flange with the appropriate fitting for what the other system is, then that's fine, because you're transitioning from one system to another with one mechanical type style fitting. But just to use one manufacturer's fitting with another manufacturer's pipe, I would not recommend that.
Got it. We got about 7 or 8 minutes left. Just as a reminder, if you've got questions for Tim and Jody, please type those in the Q&A widget below the webcast presentation. All right, guys. Are there limitations with certain fitting types, like push-on with things like vibrations?
So in regards to a Transair system, no, we have our systems anywhere from push to connect all the way to our 6-inch in high vibration applications. We have them in some railway where they're testing, they're doing maintenance, and the rails are, the trains are coming in constantly, or we have them in caves where there's a lot of vibration. Not an issue. There are some technologies where you need to leave room, as I mentioned before, for expansion and contraction. We don't, and the hangers are very important. Many times you'll see manufacturers design their hangers, example us, Transair, to go with our piping and our fittings. We leave room in this manufacturing process for expansion and contraction. We want to follow those parameters. Where we run into trouble is if we have too many 90s in an area and we create what you would call a hammer. You know, it can be done in water applications where there's water hammer, or there can be air hammer where there's too many 90s, and what's happening is the air is hitting the pipe, dead ending, and it's constant. That will shake. That will end up shaking actually the pipe, and then you can show issues. In regards to vibration, sometimes with more permanent connections, as I mentioned, ours leaves room for that. for that expansion and contraction in it. When you're soldering or you're putting on threaded connections, that's where you're going to get leaks when you're having vibration, not only with the natural occurrence of expansion and contraction, but heavy vibration will shake that up because it's not that tight of a connection. It's an MPT connection.
Can any of these design considerations be used for a natural gas system?
I would say for aluminum systems, no. I would not use an aluminum system for natural gas. We know obviously the traditional piping technologies are used for natural gas. I think that most of your modular aluminum piping manufacturers would recommend against using that medium or conveying that medium within their product.
Perfect. What is the aluminum pipe system performance in cold climate exterior installations? It says negative 40 degrees.
Yeah, so we have negative 40s outside of our range. We warranty it to negative 4, though we have outdoor applications all over the country, all the way into Canada. I have many outdoor applications in northern Minnesota. So what's going to happen is we have nitrile seals in our fittings. They're going to contract just like everything else in the winter. And then you can have some leaking. Okay, so we can heat trace these. There's ways to get around it. Negative 40 is pretty low. But what will happen is when we get within our parameters for a longer period of time, those will seal up. So it's not a disconnection concern. It's a leaking, probability. But as I mentioned, we have them all over the country outside of our parameters, but our recommendations are within, negative 4.
Got it. Is it recommended to use the rubber flexible sections for expansion joints for large runs or sections of header pipe?
Yeah, I would recommend that. There are calculations you can use to determine at what length it's best to do that. Definitely recommended to have expansion joints if you have long run. General rule of thumb, anywhere from 350 to 400 feet. There's a lot of, there's some things to take into consideration. If it's what temperature the pipe is installed at. Okay, what's the ambient temperature the pipe's installed at? What is the temperature of the facility? Is it controlled? Is it a constant facility, or is there a lot of temperature swings? Aluminum is just like any other metal material. It will expand and contract. There is design built in to the system in the fittings, and as Jody touched, with the hanger technology that we use that allows for that natural expansion and contraction of aluminum. But at some point, you will, after a long run, you will have to take into consideration expansion beyond the limitations of design. And yes, it is recommended that you use a flexible hose or flexible line to take up that movement at the end of a long run. Now, Transair does offer those expansion joints with the fittings already attached to them, so you can easily add them at any point in the installation process. But yes, definitely is recommended.
Perfect. Unfortunately, I think this is probably the last question we'll have time for. I'll try to sneak in another if I can. What is the expected lifespan of the various types of compressors?
That all varies on how they're ran. There's compressors out there 30, 40, 50 years old. It depends how they're treated. If you're in a tight room and it's an air-cooled machine that I touched on earlier, you want to have proper airflow. It depends on the maintenance that is associated with it. Remember, you're buying equipment, you have to maintain it. If it's not maintained adequately, then your maintenance costs go up, and so does your life costs go up. And I did see a question, if I can butt in here, specifications. Go on our website, you'll find us. We will send you the specifications and who to contact for technical questions. Go on that website, you'll contact us as well. We can answer anything you need.
I appreciate you doing that. That was the last question I was going to sneak in, so thanks for taking that one.
Sure.
Terrific job, gentlemen. Jody, Tim, thank you for all of your expertise. Really terrific job today.
Thank you,
everyone.
Glad we could be here.
And thank you, everyone out there, for all the great questions. Really good Q&A. Unfortunately, that's all we have time for today. Now that we are just about done, please take a moment to answer a few questions on our exit survey that's going to pop up on your screen here in just a moment. We use these answers to help make improvements to our webcast program. Finally, on behalf of Plant Engineering and Parker, thank you so much for being with us today. We'll see you next time.